Hey everybody, so welcome to our next video in stoichiometry all about limiting and excess reagents. So we've already learned about the mole ratio, which is really the most important thing to know about chemical reactions. That mole ratio is crucial in order to go from the mass of one reaction or product to the mass of another reaction or product. We've also used just regular old mole conversions in order to go from the mass of one to the moles of the other to give us these mass problems. Now, what we can do is using mass problems, we can determine how much of a reactant is left over, because sometimes you're not going to have two reactants that form the product in the most perfect ratio where there's nothing left over. Sometimes you're going to have a reactant that is in excess and something that is preventing the reaction from occurring further. You're going to hear me say the word reagent at this point in time. I'm just very comfortable saying limiting and excess reagents. It's the same thing as a reactant. It's always nice to get familiar with more vocabulary. So a reagent is the same thing as a reactant. So let's take a look at this image right here. Looks like we're reacting carbon with oxygen gas in order to produce carbon dioxide. So C plus O2 yields CO2. If we look at the amount of carbon atoms that are present and the amount of oxygen molecules that are present, in order to make carbon dioxide, one carbon atom combines with one oxygen molecule, which has two oxygen atoms in it. So if I'm making carbon dioxide, one of these carbon atoms combines with one of these molecules to produce CO2. So literally you're just sandwiching that carbon in the middle. It's a lot more complex than that in real life, but we're just kind of pretending here. So one of these gets sandwiched in between that oxygen molecule and it becomes CO2. Another one becomes sandwiched in between, it becomes CO2. This reaction is going to proceed until one of your reactants runs out. So in this case, if I have 5 carbon atoms and 10 oxygen molecules, and if they react in a 1-to-1 mole ratio, you're going to have 5 oxygen molecules left over. And that's because your 5 carbon atoms react completely with only 5 oxygen molecules. So that means that you have 5 molecules that are present in excess. There's too much of it there. There's extra oxygen left over, whereas the carbon was used up entirely. And that's the whole premise behind limiting and excess reagents. Your limiting reagent, in this case, is the carbon. It's the reactant that limits or prevents the amounts of other reactants that can combine and the amount of products that can be formed. The limiting reagent stops the reaction from happening because there is no more of it left. So carbon is your limiting reagent, whereas oxygen is in excess, and the excess reagent is not used up entirely. It's going to be left over. So carbon is your limiting reagent, and oxygen is your excess. Notice there is no free carbon left over at the end. It's because it's totally used up. It's the limiting reagent. It stopped the reaction from happening. You could make more carbon dioxide if I had more carbon, but I don't. I ran out. So it's my limiting reagent. Oxygen is in excess. And you can calculate which reagent will be limiting an excess by using stoichiometry. Again, I don't like to tell you how to do these problems. I like to show you how to do them. So let's dive in and do the next sample problems together. So notice for limiting and excess reagent problems, there are a few more steps. First step is exactly the same, right? And or balance the equation. That's always a given in any problem at this point in your chemistry career. Always make sure it's correctly balanced and written. And we're going to follow through the rest of these steps here as long as we need to use them. Again, just like I said in the last video, when you're doing these stoichiometry problems, think about what it's asking you for. You don't have to do every single one of these steps in every single problem. And you're going to see for this first one, we actually don't have to do that. So let's just dive in and do one here. We don't have to do step 1. It's already done. Let's go ahead and do sample problem 11. Silicon dioxide, or quartz, is usually quite unreactive, but reacts readily with hydrogen fluoride according to the following equation. It's given to you there. Beautiful. If 2 moles of hydrofluoric acid, 2 moles, are exposed to 4.5 moles of SiO2, silicon dioxide, which is the limiting reagent? So we want to know here which one of these, silicon dioxide or hydrofluoric acid, is the limiting reagent. And in order to do that, we have to find out how much product can each one of these form. So if I go back to these steps here, it says convert the amount of one reactant to the amount of one product. So we're going to pick one. Ultimately, it doesn't matter. Let's just pick silicon tetrafluoride here. Let's go ahead and convert the moles of silicon dioxide to moles of silicon tetrafluoride. It's not asking us for the mass. So again, make your life easy. If it's not asking for mass, don't do it. Let's just find the number of moles. So I'm going to color code these problems. It's much easier to do it that way. So 4.5 moles of SiO2. Now you could probably do this in your head. I just like to show the work so you can see where I'm getting these from. Looks like 1 mole of silicon dioxide produces 1 mole of silicon tetrafluoride, meaning that you could produce 4.5 moles of silicon tetrafluoride from 4.5 moles of silicon dioxide. However, that doesn't tell me anything because we don't know how many moles of silicon tetrafluoride can be made from 2 moles of hydrofluoric acid. So now we need a means of comparison. How many moles of silicon tetrafluoride can I make from the hydrofluoric acid that's provided? So notice step 3 says convert the amount of the second reactant to the amount of the same product. It has to be the same one. If I can compare, well, how many moles of silicon tetrafluoride can I make from the given amount of each reactant? You could figure out who produces less. And that's exactly what we're going to do. So if I have 2 moles of HF, set up a mole ratio right here. Looks like 4 moles of hydrofluoric acid produces 1 mole of silicon tetrafluoride. And when you solve for this, 2 divided by 4 is 0.5, 0.5 moles. This is where our comparison happens. We want to know who produces less product. Which of those is the limiting reagent? And we can determine that hydrofluoric acid is our limiting reagent, and that's because it produces less silicon tetrafluoride. And comparing this 0.5 moles of silicon tetrafluoride to the 4.5, this means nothing to you at that point. We needed to solve this in order to figure out who's the limiting reagent. And we found out that our limiting reagent is hydrofluoric acid, right here, HF. So the limiting reagent is hydrofluoric acid. Because it produces less product. It produces less product. I don't know why I gave you so much room to write this. We can actually, if we want to be like super precise, we could say 0.5 moles compared to the 4.5 moles. That's the answer to this question right here. The limiting reagent is hydrofluoric acid because it produces less product. The only way we can do that is by converting them to the same unit or to the same product. If I converted one to silicon tetrafluoride and the other one to water, it's like comparing apples and oranges. We have to compare it to the same unit. Now, of course, they're going to get more complex than this because, of course, there are mass problems. We didn't have to go anywhere further than this. So all this question was asking for is which is the limiting reagent. We determined the limiting reagent. It produces less product. We did not have to determine the excess reagent, and we didn't have to determine unreacted excess. So we're just going to stop there for number 11. 11 is finished. Let's go ahead and try sample problem 12. A little bit more complex here. Some rocket engines use a mixture of hydrazine and hydrogen peroxide as the propellant. The reaction is given by the following equation, balanced, good for us. Which is the limiting reagent when, it's getting back in black here, 0.750 moles of hydrazine is mixed with 0.5 moles of peroxide. We want to know which is the limiting reagent. What I like to do is I like to read through the rest of the problem because you're able to infer which product you should convert to. So A is asking what's the limiting reagent? Okay. B, how much of the excess remains unreacted? All right. How much of each product in moles is formed? Sometimes another question will ask you, like, how much water is produced? So I just like to read through the rest of what the questions are asking because if I need to eventually convert to mass of water, I'll do that in this first step because I kind of kill two birds with one stone. Doesn't look like I have to do this, so let's just make it easy. Let's just convert to moles of nitrogen. Let's start color coding here. I just picked nitrogen just because I felt like it. Let's go ahead and see, well, if I have 0.750 moles of hydrazine, how many moles of nitrogen can I make from that? You probably don't even need to do math for this because you might be able to tell what the mole ratio is, and therefore you could determine what the answer is. I'm just going to do the work for you so you could see where I'm getting these numbers from in case you're not so good with that, which is fine. So let's see. Looks like 1 mole of hydrazine produces 1 mole of nitrogen, which allows you to see that you'll produce 0.750 moles of nitrogen. That one's done. I determined how much nitrogen I can produce from that amount of hydrazine. Let's go ahead now and from this second reactant, let's see how much nitrogen I could produce from 0.5 moles of peroxide. So I'm converting it to the same product here. So I'm color coding each of these so you can see them. Moles of peroxide, not a 1-to-1 ratio here. Looks like 2 moles of peroxide will produce 1 mole of nitrogen. So my answer is 0.250. Question is asking, which is the limiting reagent? So now that I found, all right, well, I could produce 0.750 moles of nitrogen from 0.75 moles of hydrazine, but I can only produce 0.250 moles of nitrogen from 0.500 moles of peroxide. Your limiting reagent must be this peroxide. It produces less product right here. This other number means nothing to you. You just needed that in order to determine the answer to this problem. However, the question's not asking for how much is produced. It's asking for which is the limiting reagent. So be cognizant, be aware of what it's asking you. And because it's asking you for a specific reagent, write a little blurb, write a sentence, write a fragment even to answer the question. We are going to say that peroxide, H2O2, is the limiting reagent. Make sure you answer the question. So in this case, if I were to just solve what I did there, it's not really answering the question. This thing right here is, but of course you need the work in order to show that. So both of those are crucial. How much of the excess reagent in moles remains unreacted? So we have to go back to these steps here. And let's scroll back up. So we want to know how much unreacted excess is left over. And in order to do that, we have to convert the amount of limiting to the amount of excess. So it's another problem, which is, these can get very tedious, I know, but like I said, it's the name of the game, so we have to do it. We know that peroxide's the limiting reagent. So all 0.500 moles of that is getting used up. And because that's all getting used up and all of this hydrazine is not getting used, some of this is going to be left over. So we need to determine, well, how many moles of this is reacting? Because it's not all 0.750 moles of that. So we need to do another problem. We need to figure out, well, how many moles of that is actually reacting? So we need to go from the limiting reagent to your excess reagent. Again, because all 0.500 moles of this is reacting. There's none left. That's what a limiting reagent is by definition. There's none left over. So 0.500 moles of peroxide, our limiting reagent. Let's go ahead and do a mole ratio step here. Looks like 2 moles of peroxide reacts with 1 mole of hydrazine. Whoops, forgot an L there. Which this tells me that 0.250 moles of hydrazine actually reacts. 0.250 moles of hydrazine reacts here. However, that's not what the question is asking. The question is asking how much remains unreacted. So we have to consider, well, I have 0.750 moles of this available. So let's go back to black here so we don't get confused with all the colors. I have 0.750 moles of hydrazine that's available. That's how much the problem is starting us off with. That's how much is available. I'm going to subtract from that how much is actually reacting. So 0.250 moles of hydrazine is actually reacting. And we determine that from that step above, right here. So this comes from this, and this pad that I have to write on isn't always useful all the time. It's a little too small. This comes from here. So because I know how much is available, and I also know how much is reacting, I can determine how much remains unreacted at the bottom of the beaker. And in this case, 0.5 moles of hydrazine remains unreacted. unreacted. So like I said, this tells you how much is left in the bottom of the beaker after the reaction is over. This is your excess reactant here. And you find that by subtracting what's available from the problem minus how much actually reacts by going from your limiting reagent to your excess reagent. It's a lot of stuff that's happening here. So units are important. Keep track of your units. There's also steps that I gave to you on how to solve each of these. So convert amount of limiting to amount of excess. Subtract the amount of excess reagent needed to react in step 6, so that's what you found, from the amount given in the problem. It tells you step by step how to do everything there. Try sample problem C. How much of each product in moles is formed? We already know the answer to 1 because look, I already solved it. I'm actually going to go back to that color here so we can see that. I already know, put my answer on off to this side. Well, I'll do it over here, I guess. We already know 1, 0.250 moles of nitrogen. Keep forgetting that L. We also want to know our other product though. So my other product is water, which guess what? We have to do another mole ratio step. How much water could be produced? I don't know if I have enough room here. We have to go from the limiting. It's always from the limiting to your other product. So how much water can be produced from this limiting reagent? You will always go from the limiting. Look how many arrows are coming from this limiting reagent right here. So limiting to the excess, limiting to one product, limiting to the other product. You only needed to do this first one, this one in orange, in order to determine that that's the excess reagent. Let's go ahead and solve right here. So I have it in green, which I'm ready to go. I'm starting off with 0.500 moles of peroxide. Looks like 2 moles of peroxide produces 4 moles of water. Looks like my final answer is 1 mole. 1.00 moles of water. And that's my other answer. Oh boy. So that guy and this guy. These take practice. If you're overwhelmed, that's okay. This takes a lot of practice to get good at them. That's why we're going to do quite a bit of these, not just in these videos, but you're going to do a lot in class with me as well. You're going to do a lot of these in labs. You have to get good at this process. And like I said, by the end of this unit, I've been teaching Chem 2 now for quite many years, quite a lot of years. And I've never had any student that has not mastered stoichiometry by the end of this unit. So if you are overwhelmed, that's okay. You're not going to be overwhelmed in a couple of days. Write down any notes you have. Ask me questions the next time you see me. It's very important to ask questions, especially with this. I mean, look at all this stuff I have on the screen. There's a lot of colors. There's arrows. There's a lot of different equations, lots of different calculations. Ask me questions. Let's do one more. Like I said, I don't like to make these videos too long, but we do have to get problems done. Here we go. The black oxide of iron, Fe3O4, occurs in nature as the mineral magnetite. This substance can also be made in a lab by the reaction between red-hot iron and steam, according to the following equation. When 36 grams, let's get black here, the base color. When 36 grams of water is reacted with 167 grams of iron, which is the limiting reagent. Again, let's read through the rest of the problem just to determine, do I need to convert to a specific product? And if I look at question B, what mass in grams of black iron oxide is produced? We're going to convert to this product here because once I solve A, I actually already have the answer for B. So we're going to choose this product here to convert to. Already balanced, that's great. Let's go ahead and start color coding. So let's convert iron to iron oxide first. Say, all right, I have 167 grams of iron. How much of that black iron oxide can I produce from that? So 167 grams of iron, 55.85 grams of iron is equivalent to 1 mole of iron. Look at that mole ratio next. 3 moles of iron produces 1 mole of iron oxide, and 1 mole of iron oxide has a mass of 231.55 grams. And when you solve for this, you should get an answer of 231. So 231. I could produce 231 grams of iron oxide from 167 grams of iron. That doesn't tell me the answer though. Now we need to figure out, well, from 36 grams of water, how much of that product can I produce? So same exact thing, 36 grams of water. Oh wow, that's quite a line there. All right, molar mass is 18.02. 1 mole. Water. Looks like 4 moles of water produces 1 mole of iron oxide. Since we found the molar mass already, I don't have to calculate that again. I'm just going to look at the problem above because this part should be exactly the same. 231.55 grams. And when you solve for this, you should get 116 grams. So question is asking, which is the limiting reagent? In this case, who produces less of the product? You should say water. Your 36 grams of water produces less of the iron 3 oxide. At this point, this number means nothing to you. You needed to find that though in order to compare and to determine which is the limiting reagent. In order to properly answer this question, let's write a little fragment. Let's just say water is the limiting reagent because that will answer this question sufficiently. So we'll say water, H2O, is the limiting reagent. Now, just by writing water is a limiting reagent without any work is not going to get you any points because you got to mathematically show that as well. B, what mass in grams of black iron oxide is produced? You already did that because look, we solved that up above. Don't make any more work for yourself than you need to. This is the answer. So I'm just going to write 116 grams down below. That's why I like to usually read the whole problem first, because then I don't have to do more work than I need to. If you solved for hydrogen, you'd have to go ahead and do this one again. And why do more work for yourself than you need to? Last one here, C, what mass in grams of excess reactant remains unreacted when it's completed? So we've determined that iron is my excess reagent. There is some iron left over in the beaker when this reaction is done. Not all 167 grams of that is reacting. So we need to determine, all right, well, from this limiting reagent, because all of this water is being used, that's what the limiting reagent is. How much of that iron is actually reacting? Because it's not all 167 grams. All 36 grams of water is reacting, but not all of that iron. Let's do another mass problem here. Just going to scroll down that much so I could still see the reaction right there. 36 grams of water. 36.0 grams of water. Once you get to this point, you should have all of the molar, or at least most of the molar masses done already or calculated already. So like water, I already have. It's right here. So again, don't make more work for yourself than you need to. 18.02 grams of water is equal to 1 mole of water. Looks like 4 moles of water reacts with 3 moles of iron in this reaction. And 1 mole of iron has a mass of 55.85 grams of iron. Once you get all that down, you can solve to find out, okay, well, how much of that iron is reacting? So when I do all of the work here, which I'm typing in on my calculator, on my phone, which I highly recommend not doing this on the phone because you don't get, I tend to not like it. 85. You should get 83.7. 83.7 grams of iron. This is how much actually reacts with all of that limiting reagent. 36 grams of water reacts with 83.7 grams of iron. Question's not asking for how much reacts. It wants to know how much is unreacted when the reaction is completed. So we have to consider how much is given to us. There's 167 grams total. So 167 grams of iron is available. From that, we're going to subtract how much actually reacts. That's the 83.7 grams of iron actually reacts, which this could tell us how much remains unreacted at the end. We do want to adhere to significant figure rules here. And since we are subtracting, we basically need to knock off the decimal place. So 167 minus that 83.7 gives me 83.3, but knock off that 3, so it's just 83 grams of iron. This is how much remains unreacted. Unreacted. This is how much you'll have sitting at the bottom of whatever vessel you're doing this in. Is this easy? No. It's not hard. It just takes a lot of practice. Like I said, if you're a little overwhelmed, that's okay. That's what happens when we get to this point. But like I said, you will not be left behind at the end of the stoichiometry unit. You're going to get so much practice with this. You're going to be doing stoichiometry in your sleep. So no worries. Ask me any questions. See me before or after class, during lunch, whatever works for you. And I will see you in the last video in this stoichiometry series, which is actually quite simple. It is percent yield. I think you'll get a nice little break from all of this stuff. Much easier than what we were doing today. I hope you have a wonderful day, and I will talk to you soon. Bye.